Oh, no. Okay. Is about right? Okay. So first of all, I like to just take a picture so then I always forget, but today I'm like, oh yeah, let me remember. So let me take a picture, selfie. Okay. Hello, can you hear me okay here? Okay, yeah, okay. I'll just take a selfie first, yeah, okay. Okay, yeah, I'll take one more. Thank you. Okay, so let me make sure. Oh, point at this, okay. Make sure, okay. Okay, so want to make sure, I think I can start now, or should I start now? Something. Oh, the mouthpieces. Thank you. Yeah, okay. So you can hear me okay. Folks at the back too, can you hear me okay? Yeah, okay, great, yeah. So I can start now, right? Yeah, okay, great. So first of all, thank you so much for coming to my talk. I know that right now Venkat is speaking too. So at first when I look at the schedule, I said, I got Venkat next door. I know Venkat very well. He's a very nice person. So I was thinking, maybe nobody comes to my talk. But to see you all here, so thank you very much. I really appreciate this. So yeah, so my name is Mary Grygleski. I'm from Chicago, and I work for IBM. I'm a developer advocate. As such, I do a lot of outreach work, so talk about topics. And right now, my topic is on reactive Java. So that's what I do. And also, in my spare time, or actually when I'm not working, I'm a Java developer, or actually I should say I'm an organizer for the Chicago Java Users Group. And actually, you have someone too from Belarus who came to Chicago too and visit us. So I invite all of you too, if you come to Chicago, come to our Chicago Java Users Group and visit us too. So I encourage all of you too to participate in the community. That's a good way to share information and everybody grow together. It's always very good. I think it makes the community really lively. So yeah, so that's one thing. So now I'll start my talk. So my talk today it's about reactive Java programming and reactive systems. As such, it's just a very, let me make sure I can get to the next slide. Sorry. Am I pointing at the right thing? Oh, this way? Okay. Okay, sorry. So I just want to make sure I point to the right thing. Is that I'm just going to talk about, it's really a gentle introduction to this topic. And then I'll also do a survey on 4 of the popular Java tools and libraries: RxJava, Spring Reactor, Akka, and Eclipse Vert.x. And may I first ask you, how many of you have already worked with reactive programming and systems here? Yeah. Oh, so quite a lot of you. So maybe you can also, yeah. So this may become kind of a bit of an introduction rather than as deep dive. But as such too, I will kind of touch upon a lot of different libraries. So first of all, we'll talk about why reactive. So reactive programming, reactive systems are not all brand new. I mean, they came out actually at the very early too. For example, actor model came out in the 80s from Erlang, the actor model. That one, because there's also a need for it, because of, especially for telecommunications, everything needs to be happening right away, the real-time communication. So why all of a sudden, why reactive right now? Okay. So the reason is that there are a lot of changes in the marketplace. First of all, we have hardware level changes. For example, right now there's CPU, the clock speed. There are multi-core CPU, and multi-CPU and hyper-threading. All of these, they are making it the hardware be really ready for software to take advantage of. And of course, too, there are also virtualization, containers, all of the infrastructure, cloud strategies. All of these is actually making it kind of more pertinent that software needs to get caught up. And of course, too, as such, the title of my talk, too, I call it Reactive for the Impatient, because ultimately it's us. We are the very impatient human beings that we want things to be done soon. We don't want things to be done right away. We want it to react faster. So in some ways, too, there's a really drive for it. And not only that, if you think about it nowadays, every household, we have not only like one person have a cell phone, every family member will have multiple devices. So can you imagine, like in that case, then all of the needs for accessing the network and everything needs to be a lot more, needs to be more responsive and be able to react to requests a lot faster. And also the fact that there are many requests coming in, then there's got to be better ways of handling if there are failures too. That all these things are actually reactive systems. It's like making it possible. And I'll go on to talk about what is reactive systems. Okay, so what is reactive, right? So, oops. Okay. So I just want to point out, first of all, there's a reactive manifesto in here. It's actually a set of guidelines and principles. So if you're not familiar with it yet, you can visit this link, and that will explain to you the Reactive Manifesto. Essentially, there are like 4 main principles. But first of all, the last version came out in September of 2014. It's version 2.0. It's essentially just more flexible systems and able to tolerate failures a lot better and handle failures a lot more efficiently. Okay, so the 4 core principles of programming reactive systems, first of all, is being responsive. So by being responsive, it means that requests coming into a system that will be handled in a very timely fashion. So response will come out too in a very timely fashion as well. Even though there's wait time, is probably more like acceptable kind of response time. And another principle of it is about the elastic principle. And that part is basically deal with when system is under load, then there should be more resources to handle it. So think of the elastic band. So there are more resources, more requests coming in, then there would be more resources. For example, in an actor system too, like Akka, then there will be more actors probably spin up to handle all of these requests coming in. And then if your requests fall below, then basically all of your resources will need to also return back to doing something else. So it's very elastic. So overall, the throughput of a system should not suffer under varying loads. So the throughput should stay the same. Essentially, that's what elasticity is. And then another thing is, the third principle here is resiliency. By resilient, it means that system needs to be able to recover under failure condition. So in failures itself too, it's like an event inside reactive systems. They are like first-class citizen. So if you think of in normal Java traditional programming, it's if you have failures, then we normally have to handle doing try-catch and doing all of these things. But in a reactive systems, failures come in as just another event that needs to be handled accordingly. And the response time of handling failures also should not suffer as well. So that's what the responsiveness also needs to happen in a failure situation and making the system a lot more resilient. So all of these principles are made possible because the systems itself is a very message-driven system. Message-driven enables a system that's having multiple different disparate components being able to communicate with one another. That's like a communication mechanism that's message-driven. As such, too, message-driven has it knows where the message needs to go to, and it handles location transparency for your whole system. And that's what, essentially, summarizing, that's what message-driven is. So these are the 4 principles of that must have in a reactive systems. Okay, so just something to point out is some important distinctions too. Essentially, you have all heard of reactive. Reactive is everywhere now. There's reactive programming, there's also functional reactive programming and reactive systems and architecture. So when I first kind of picked up this topic too, it was confusing to me. So I thought it might be worth a slide just to point out. So it's like fruit, right? We look at fruit, they look the same, but they are not the same. So reactive programming, So what the one distinctive thing is that in reactive programming, you have a flow, a control of your systems that flow. What drives this flow is really the events that come in, so the data changes. When the data change, it drives the logic forward. However, in functional reactive programming, it's like any kind of programming, you're doing functional programming, is basically the thread of execution will drive the logic forward. So there's a distinction between the two. And then in reactive systems and architecture, reactive systems really is another level up of systems of reactivity. It don't not only deal with one component like in reactive programming or functional reactive programming. We're concerned with like multiple, like a big ecosystem of many components. That's what like reactive systems is. So there will be like a lot of mechanism that needs to handle how components all interact together without collision, without colliding with one another. Things are happening in a very synchronized fashion, but they are all happening asynchronously, each one of them, the processing. But the system needs to be able to handle itself like in a very like coordinated way. And that's what like reactive systems and architecture essentially means. And one thing I like to point out too, I was actually in India for a great Indian developer summit in April. And I was explaining reactive programming, reactive systems. And if you have been to India, you may be aware that in India, a lot of the roads in Bangalore, there are no traffic lights. There are no traffic lanes. So when you cross the street, you're like, you have to basically run across the street. But think of, in some ways too, it's a very primitive way. I'm trying to explain reactive systems. I thought it's a good way of explaining comparing crossing the street in Bangalore with reactive systems. So in computing terms, you're trying to do things. Everybody is acting differently. You have you have cars on the road, you have buses, you have bikes, motorcycles, everything running on the streets. But some ways too, nobody get hurt because there's got to be some mechanism that kind of makes all of these things happening, and you can still cross the street. And that's essentially, in some very primitive way, it's like reactive computing. And there are back pressure built up too. If you try to cross the road and you stop the traffic, then back pressure built up, right? That type of stuff. So in some ways, it's kind of a reactive systems, reactive programming principle being live out in a traffic system. So, so I thought I'd point out, but okay, oops. Okay, so one thing I like to point out too is to explain to you about event-driven versus message-driven. So essentially, reactive programming is event-driven, reactive systems. And then it's enabled by a message-driven nature. So there are important distinctions between the two. So for event-driven, and by the way, this diagram I took actually out of the Lightband documentation. So to explain event-driven, so look at like events are like being emitted out from the component itself. There are some events happening. So it's like a soapbox. We're announcing something happening. But the thing is, the message doesn't have an address with it. It's just like messages. It's the old like messaging system, right? There are publish, subscribe. Messages being published. And it doesn't tell where to go to. Because, why? Because it's up to the people interested in it, like basically the observers interested in it. So in reactive systems and programming, we're using terms like observables and observers. Observables are like events being published, and then observers are the ones interested in your events. They are ones observing and basically do something about it. So that's event-driven. However, for message-driven over here, message-driven has like a specific, like addressable component to it too. So their messages is like comparing with two people talking. So they know the messages are going to the other person. So there's a definite like destination of your message. And I'm replacing with actually envelopes. It's like soap envelope, the old style soap, right, Whistle web services. But here too, message-driven essentially has an address associated with your message. So that's like the important distinction between the two. Okay, and here, before, I know it's almost lunch, because I know too I was talking about all those previous like concepts. Some of you are probably thinking, oh, I already know, it's kind of boring, right? So I thought, well, okay, let me kind of pique your interest, get you not falling asleep yet. It's basically, I wanted to describe too like like a computing case, like a use case that we can employ this principle of using like reactive systems. So, and I was actually in Tokyo back in December. In Japan there are a lot of noodle shop. So I wanted to kind of point out this example as something we can kind of turn it into use reactive programming, turn it into a systems. But for now, I won't go into details yet, but I just want to get you interested, and that's what I'll be talking about this use case in a few slides. So. Okay, so first I'll go back to some talking again about reactive programming. So there are some patterns and terminologies. So we have reactivity. So reactivity is really the process of responding to external stimuli and propagating events. And the events themselves are stimuli. And streams is also like one important aspect of reactive programming and systems. Streams are really primitive representations of a sequence of data elements. And the observable, as I mentioned earlier too, they are really stream of events. And the design patterns being used, they are observer, composite, and iterator. Those are common Java patterns, which I won't go into details. So, okay. And now goes back to a bit of reactive programming. So I'm using these RX marble diagram borrowed from the reactive extension. So think of like reactive programming is like events streams on a timeline. So over here we have, these are basic, by the way, this basic programming primitives, right? So we're talking about streams. In this case, the top one is just a stream. It's like basically waiting for events. So no events yet. And then if you go to the second one here, you see some different shapes. Those are the marbles. These represent like events. And over here, there's like a perpendicular line, not a shape. That means that the stream itself has terminated. There's a definite timeline to this stream. And the third one here is another set of streams with events. And over here, there's an X in here. The X indicates a failure event. So failure itself is a first-class citizen. It's just another event that happened. So when it happens and something it indicates that it needs to be handled correctly. Basically, it trigger another action, but basically have to handle this error condition. And the bottom here, too, is another like stream with the different events. But in this case, nothing happens in here. The reason is that this is an open-ended stream. It just continuously receives events, is what it is. And here, too, is another example of just a very basic operator taken from like RX Java. It's using the map operator. So to explain this, using that timeline, then here we have an example of like 1, 2, and 3. Like those are events with data coming in. So we basically use map. Map is a data transformer. So over here, the map is basically telling it to multiply whatever comes in, multiply by 10. So this is just a simple example to illustrate. And so after you actually execute all of these, right, then what will happen is you see that the result of this will be like 10, 20, and 30. So in coding terms, and over here, we're using observable, doing a dot just, and then we pass in the events. Basically, these are input, right? Input in the stream has 1, 2, and 3. And then you apply the dot map, and that's like transformed data. You multiply by 10 here. And then immediately, too, you're basically the consumer of this whole processing in here is right here, because we're doing a dot subscribe. The subscribe will basically, in this particular case, just print out the result. Like over here, it's just timber.d is item. And so you see the output is item 10 and item 20 and item 30. So this is just an example to show you reactive programming. And of course, there are operators such as like flat map, filter, and all of the other ones too. And you are all kind of, if you haven't done it and if you're interested, you can all visit. There's a rxmarbles.com too. That actually has a site with all of the example of all of the operators. You can actually play with it like interactively too. Oops. Okay. Now, I'll go on then to talk about reactive systems, design and patterns. Here, I won't go into all the details, but essentially, too, there are like 6 major category of patterns to handle reactive systems. So state management and persistent patterns. So there will be like design patterns such as like domain object, sharding, event sourcing, and event streaming. These are like the state management and persistent patterns. Then there are also flow patterns like pull, manage queue, drop, and throttling. And then there's also message flow patterns like request, response, self-contained message, ask pattern, forward flow, saga pattern, business handshake. These are more message flow patterns. And then there are also fault tolerance and recovery patterns, such as like simple component, error kernel, let it crash, and circuit breaker too. And also then there are also replication patterns like active-active, active-passive. Then for resource management, there are like resource encapsulation, resource pool, and managed blocking, and complex command. So all of these two are, actually, there's a book called Reactive Systems Design that actually documented kind of write-up of all of these patterns in a lot of details. And I have that link towards the end of my slide that you can also like get into detail if you're interested. And then the next one. Just wanted to point out too, in reactive systems design, some terminologies. We're talking about also reactive microservices versus monoliths. So basically, in today's world, we are also like talking a lot about breaking up monolith systems into like microservices. And then we can also like use like reactive, like basically utilize like reactive style in your microservices as well. So that's as such is for utilizing the event-driven, asynchronous, non-blocking nature of reactive systems. And I'll go into a little more detail in a little bit. Then there's also essentially reactive systems are basically dealing with like the isolation of state, space, time, and failure in your system. And some interesting patterns that I mentioned earlier, I just want to point out is the circuit breakers. So circuit breakers are essentially, conceptually, is that if there are any failure in the systems that's happening, then there's got to be some way of basically breaking the failures and not letting it kind of continue. So then your system can then proceed normally, because the responsiveness needs to kind of stay kind of very highly responsive. So there's got to be a circuit breaker mechanism to handle this failure situation. And then there's also back pressure. Back pressure as such is when there are too many requests coming in and the component fails to handle it in a responsive manner. So a very good reactive system then should have mechanism of basically handling it accordingly. For example, like Akka, which actually IBM has a partnership with Lightband. Akka system has a supervisor capability. So basically, if there are errors that happen, then basically the actor itself will then maybe spin up more actors to handle all of the requests, and if not, maybe slow down the input coming in. So those are like different mechanisms that to handle it, and as such, those are like back pressure situation. And then there's also high availability and eventual consistency, and this CAP theorem I just want to point out too. So in CAP theorem, basically the theory is that there are three aspects of any data-intensive systems. Three aspects. One is a network partition, network connectivity, and then there's high availability of the data, as well as consistency, integrity of the data. So CAP theorem is saying that of all three, only two can happen at one time. And network partition is a given. It's always, it's connected. So then that means either high availability or eventual consistency one of them needs to relax and kind of not, be so accurate. And because in reactive systems, the responsiveness is very important. So a lot of times too, we probably can tolerate a bit of like inconsistency or kind of inaccuracy in your data. Why? Because we believe that there are constant update to our systems. But at some point, too, the update will slow down. So if you keep querying your system, you will eventually get data that's accurate at some point. So then you always go for high availability first. So that's what it is, and I just wanted to kind of point this out too. And so another thing about in reactive systems in this whole area, there's a specifications. It's called reactive streams. And what it is basically just a standard for asynchronous stream processing with non-blocking back pressure. And currently it's at specification 1.0, and its basically release was in 2017, the latest release. So they are actually led by Lightband and Pivotal and Netflix, and then now also Oracle, Twitter, and Red Hat Spray.io also has joined too. And basically, RX Java supports it only like partially, and Spring Reactive supports it fully. Because Spring Reactor actually came later, like after Java 8. Actually, that one they support it fully, and so is like Akka also supports this fully too. Okay, so a bit too about like, what about microservices? So reactive programming is being used within a single microservice. It's used inside a single microservice because it's used for implementing like service internal logic, and that manages the data flow. But reactive systems is basically used in between the microservices because it enables all of the components to kind of communicate with each other. So it's really like a way of bridging, like a microservices ecosystem is what reactive systems is. So that's just something. Okay, so also one thing to point out too is that in Akka, in the whole Akka Lightband product offering, there's a Lagom. Lagom is a reactive microservices framework, and it's built on the Play framework and Akka cluster, and it has RPC-style programming style, and has a message broker API that's implemented in Akka streams and Kafka. And the persistence too is based on the concepts of entities and domain-driven design. And so it actually supports like event sourcing and CQRS too, which is command query responsibility segregation. Okay, so now I'll go back then, kind of back to my the Japanese noodles slide. So here I just want to explain to why I thought of using like reactive programming to implement this system. So you go into a noodle shop in Japan there. There's usually nobody there to serve you because what they have is just a vending machine. So you can imagine too, it's one vending machine, and you go into the noodle shop and you punch in your order. Think of how inefficient it is in computing terms. It's entirely like a blocking type of operation. You go in one system, that's the only single source of input. So you punch in your order, and then you put in your money. It doesn't even take credit card, right? And then it comes out, you get the tickets, and then basically you take the tickets to the server. So over here. So can you imagine it's in a computing term, again, it's very inefficient, it's blocking. You go in, and as us, right, we're busy programmers, we don't want to waste time. We want to be doing something else. We want to process things in a very asynchronous manner. Meaning we submit our order, we go back to do our programming, and in the meantime, the noodles are being prepared. We don't care, we just kind of submit our order and wait. So that's what I was kind of thinking, right? So, oops. So here, I scribble on a piece of napkin when I was there, thinking, this will be a good way of using reactive programming. So over here, it's like, scribble on this napkin. I'm thinking, okay, we are customers coming in, placing an order. So how about we have a mobile app that's basically take the order? So us, as busy programmer, we are at our desk, and then we're programming. We say, let's pull up I'm hungry. Let me pull up my mobile app and place my order. So those kind of think of the orders is like order event coming in. They are observables. And basically then will be the observers, will be the waiters at the restaurant, then will take your order. But in the meantime, they can't really tell the cook to cook the noodles yet. Because, why? Because there are no seats available. And by the way, too, there are no regular seats. So it's like a bar area. They cook the noodles, they just serve you. You eat right basically next to the kitchen area. So you do need to wait for a seat to open up. So in this case, then the waiters will then have another responsibility is to wait for a seat to open up. So I also have another observables basically to receive event that tells me that when there's a seat open up. So in this case, the waiters will have to then say, okay, an order comes in, and I want to make sure there's a seat available, then I match them up. And in this case, if both have that, then I can tell the cook, the chef to like cook the ramen. And in the meantime, then I'm thinking, we can have some sort of notifications too that basically send to us, the busy programmer who placed the order, and said, okay, well, the noodles are being cooked, so I know, okay, in about 5 minutes or 10 minutes, it will be ready. So in the meantime, I'm busy. I can then compile my program or do whatever is needed, finish it with 10 minutes, then I know I have my food. So in the meantime, then I can basically then go to the restaurant. And so when the noodles are ready, then I'll be notified, essentially. They notify and I'm there. Then I say, oh, cool, my program is done or is working, and let me go to my noodle shop, and I can sit down and eat. So that was just an idea that I come up with, that maybe I can implement a system like that takes care of this whole ordering system without wasting time. It's a very non-blocking manner in computing terms. So that's essentially what I think of. It's the nice thing about reactive systems is it helps you to save time because requests are being processed, and you can then do something else and not have to wait for it. It's basically the main thing about it too. So now I think I only have maybe 15 minutes or so, right? And so I'll go into the last part of my presentation, which is about the 4 different libraries, the common libraries. First is RxJava. So RxJava is a Java implementation of Reactive extension, and that's the link to it. And it's very popular, especially on Android. And it's also available in JavaScript, in .NET, Scala, Clojure, Swift, and more with the equivalent API. And the version 1 itself, it's before the Reactive Stream specification in 2014. And 2016 came out with the flowable with back pressure as well. So here's just a code example. Here too, because I'm comparing all of these, I wanted to do some kind of simpler example. So Hello World, for example, here. So you can see too with Hello World in here, think of how in traditional systems, then it needs more command statements too. But over here, using reactive programming, it's basically one command statement. You can take care of the whole thing. Of course, it's a simple case. So essentially, you can do a flowable dot from array, take the argument, and basically do a subscribe right here. The subscribe will essentially, what it does is just outprint, doing a print line, doing a system out print line, and basically print it out hello, whatever it gets passed in. So it's one thing about reactive programming is that it basically, as compared with traditional style programming, is a lot more cleaner, it's more elegant. You don't need, on a programming perspective, you don't need that many command lines. You can have chain all your commands together. So that's I want to highlight that part of reactive programming. And actually, even Venkat has pointed out too, if you've been to his talk before, he feels that reactive programming will probably be the programming, the style of programming in the future. That declarative style should kind of get caught on. And it will take some time for everybody to get used to, because we're so used to traditional style of programming. But here too is just an example of using RxJava. And here too is also another example, but here it's not even a program in here. It's just wanted to point out how do you attach a producer to a consumer. So earlier too, I already showed it's basically observable. Doing a .just is like your list of events here. And then your consumer will then tell it what to do. In this case, it's a system.out.println. And to attach the producer to the consumer, you can just do an observable.subscribe and pass in the consumer. And that's how you do it in RxJava. Okay, so next will be Spring Reactor. So Spring Reactor is it's based on Project Reactor that came out from Pivotal. And it's very similar API to RxJava 2. And it's built for Java 8 and above. It came out, Spring Reactor came out since Java 8. So it has a more cleaner interface because it was able to take advantage of the streams of the functional style of programming in Java 8. And also, here too, I'm quoting this is David Cannock, who's a project lead for RxJava. He also contributes to the Reactor. So you'll find that actually RxJava 2 and Spring Reactor, they are similar because they actually have a similar group of engineers working on both. And so just a quote in here is David Cannock said, use Reactor 3 if you're allowed to use Java 8 and above. And use RxJava 2 if you're stuck on Java 6 or need your functions to throw checked exceptions. And then all these two are all the libraries within Spring Reactor. And then to do your programming, essentially you use the Reactor core. But you can also see that it also has its test libraries as extra and good integration with Netty, with Adapter, Kafka, and RabbitMQ as well. So here are just some code examples too, is that using Spring Web Reactive, which is a non-blocking web stack. So here I just doing a simple example, comparing. So in the top one is the traditional approach of using Spring MVC. So over here, they look the same, the two sets of programming, but if you look in the above, over here too, you will see that first you will see traditional way started, and then you make a call to get products, and returns a list of products. However, in this case, it's a block. The traditional style is really blocking call. So you basically do a get products. Your method will then block in this case, waiting for the list of products to come back. And when you get the list of products, then you will see traditional way completed. And that's, again, the traditional way. However, if you look into the reactive approach, which is using like the Spring Web Reactive Web Flux, over here too, basically you do a get mapping here, and here I wanted to point out, in this case, we're using a text event stream value. This one was basically indicate that the client who is interested in the results can actually subscribe to a server send event. So basically, you can make your client, the whole thing to kind of act in a most reactive way is for your client to also subscribe to the results, the response to, again, to subscribe to this server send event. It's essentially in order to get the response back. But I just wanted to point this out. So anyway, so using Flux, right, you see that here we have a system print line saying like reactive way using Flux started. Then we go and do a get product stream call. And this one will return the Flux. But the Flux too, in this case, you'll get the Flux back. And think of a Flux is just like a ticket. You get it back a handle. In this case, what will happen is that your method will keep going, and you get your Flux back, and then you will actually see reactive way using Flux completed. But at that point, you don't have your result yet, because what will happen is that this is all non-blocking, asynchronous. Then you just hold on to your Flux. And the Flux will eventually, when it happens, it's just like a sync, right? When it completes, then the result will kind of a standard way go back to your client in HTTP, for example. But like I said, if to make it more reactive, your client can also subscribe to the server send event. In that case, then your client will have to deal with the response coming back. So there are like different ways of how you can get back the results. But the point is that using Web Flux, using Spring Web Reactive is a very non-blocking way that is really the true reactive way of handling this call. So, okay. Okay. So now, just a quick comparison then for RxJava and Spring Reactor. I already talked about most of it, but just wanted to point out again that RxJava started in Java 6, and the Spring Reactor started in Java 8. They're both single-threaded, non-blocking, event-driven. And Spring Reactor will support reactive streams fully, but RxJava only supports reactive streams partially. And some of these things, these are just like standard kind of comparison. But again, the slides will be available later. So. And next, I'll kind of talk a few minutes too about Akka. Akka is from Lightband, and IBM has a partnership with Lightband too since 2017. And Akka makes use of the actor model. Actor model is not new. It's actually come out of Erlang in the 80s too. And it's event-driven and location transparency and the lightweight of it. That's what's really attractive about it. Also, the resiliency recoverability is really greatly enhanced by its supervisor capability as well. So here, I'll also move on to another example, which is at Hello World, again, an example, but using Akka. You'll find that it will take more coding, more classes because of the actor model, but I just want to illustrate this. And again, this also is taken from the Lightband documentation as well. So you see that in here, in the main, in here, all you do is just you basically start off your actor, the Hello World actor, and that's what it is needed. So we'll then take a look into the Hello World actor. So over here too, you look at that. Hello World will extend abstract actor. And by the way, this is in Java, so I'm using Java. So you see that there are more code too because of Java. But I'll show you another slide using Scala, just so you know. So over here too, we just want to pay attention to the pre-start in here. So the pre-start was basically, over here too, what it does, the Hello World will then basically get the context and basically create a new actor, which is called the greeter in here. So the greeter will basically then print itself, and when it's received the request to do it, then the greeter will then print itself out. So this is like the main thing. Just want to make sure that's right. Yeah. Okay. Okay. And now let's take a look at the greeter. So the greeter itself too, when it's being called, and basically it starts, and it starts itself. It gets started. If you remember, when the main will call the Hello World actor, Hello World will then instantiate this greeter. So the greeter itself too, it starts, and basically then will be there just waiting for commands, waiting for requests to come in. So when it receives a command, then what it does is that it will just let's see. So somebody sends it a message, then the greeter will basically react to it. And basically it goes, and over here too, it does a system out print line, hello world. Over here, that's sender.tell, and basically prints itself out, tells who it is, right? So you can see too in Akka, and probably will take a bit more code. It's because of the actor model. You need to have different actors that handles different functions within your purpose of your application. So, and here too is an example then in Scala. It's essentially the same thing as Hello World, but as you can see too in Scala, it's fewer lines of code as such. So and it's just a nicer. Much nicer kind of interface. But my talk too is about Java, so I won't go into as much detail. But over here too, the Hello Akka is basically extends app, and doing an actor system is basically you do a greeter over here, and basically that's what it is. So Scala, as you can see, it's built more to enable reactive systems to being done in a more efficient manner as well. So. Okay, so now I'll come to the last part, the last example. Here is with Vert.x. Vert.x comes from Eclipse, and the nice thing about Vert.x is that it's very polyglot in nature, meaning that you can actually have Vert.x and then call JavaScript, call Ruby, for example. It's a very polyglot framework. The Vert.x doesn't use actor model, but it uses a model called verticals. Verticals is basically, it's similar. It kind of acts similar to actor too, but it's not actor. So verticals are components that are being deployed and executed by Vert.x. It's very event-driven, and it runs only when it receives a message. And essentially, the Vert.x event bus handles all of the events of it. And the nice thing again, is that it's not restrictively tied to any container. The Vert.x libraries can be used with other libraries. So that's a more powerful case about it. It's because of its polyglot nature. And it's also newest too among all four libraries too. But it's also becoming more popular too in this state because it's very easy to use too. Not easy in the sense it's not as ceremonial as some of the other libraries, for example. So, oops. Okay, so now there's just an example too of Hello World in Vert.x. Over here too, you can see, in this case is that I'm using a Vert.x and basically do another Vert.x and create the HTTP server. And you basically, again, it's very efficient. You can do a .request handler in here and takes in basically the request and basically takes in the response in here and basically will print out Hello World. And then you do a listen on which binds your HTTP server, binds it to port 8080 is what it is. So as you can see, too, Vert.x itself it's very efficient to the style that you can use it. So, okay, so now it comes to almost the end of my talk here. Just want to do a quick recap and takeaways. So Reactive, again, is an overloaded world in today's market. Here, I just want to point out for those of you who haven't done Reactive and wanted to start learning about it, just don't feel discouraged because in the beginning you may find doing declarative style of programming is a little bit different than traditional style. But it will take some time. You just work on it, you will eventually get it, then it will become a lot more smoother. And so some of these things, I've kind of pointed out the differences between that and benefits of reactive programming. And basically, okay, so the last one, actually, I wanted to point out is reactivity to this day is not really fully reactive. The reason is that to claim a system, an ecosystem, to be fully reactive, like all your layers of systems needs to act in a reactive manner. But in today's world, the database engines, none of the relational database engines are actually fully, none of them have reactive capability because they are still using blocking I/O. So in that sense, is that just keep in mind that it's not, fully like asynchronous for a database engine level. However, you maybe have heard too there are database connectivity libraries. For example, Spring. I think Josh Long is here too. They talk about the R2DBC. That's reactive, is non-blocking I/O, but that's for database connectivity. But once you connect to the database itself, it still goes into blocking. So that's something I like to point out to you. And that's something too, I'm also starting to put together a virtual reactive user group that I would like to invite folks from the database vendor maybe to talk about, is it ever possible, for example, to have a non-blocking I/O database engine? Questions like that for reactive systems of the future. So please stay tuned for that too. If you follow me on Twitter and stuff, I'll announce it. Once I set up my online user group, then I will announce it. So, yeah. Okay. So thank you very much for coming, and this is how how to connect to me using Twitter or GitHub or also my profiles on the IBMdeveloper.com. But I would like to invite all of you to sign up if you haven't already done so. There's an IBM Cloud we offer like free tier access to, so you can sign up for your IBM Cloud, and then you can do things on your own and do any kind of your own experiment. There's like certain parts of our system, because IBM, as you know, there are many like components underneath, many different like AI, the Watson, the machine learning, and everything, right? For IBM, it's like a big toolbox. So not everything is free, but then you have a free tier access to some of the things, and also some of the stuff too, it's maybe a limited time of free access too. So I encourage all of you to sign up for it, and it doesn't cost you anything. And even if it expires, after 1 year for certain free things, you can still use it too. So that's the nice thing about it. So I like to invite all of you to try that. So this is the link to it, this short link. And then this is the link to all of the reactive systems right now. Our group too is actually starting to build up the reactive systems resources. So please check that out. Eventually we'll fill it with more information and light then too, and we'll also be contributing to contents in that website. And then all these are the links to the different things I've talked about in my talk here. The bottom one is the reactivedesignpatterns.com, and that one explains all of the reactive systems design in a lot of details. It's real good, so. And yeah, thank you. Thank you. So I just have like maybe 2-3 more minutes, but just wanted to point out and invite all of you too, if you are interested, to sign up for IBM. There's a multi-year initiative for a good cause. It's called callforcode.org. If you haven't already heard about it, it's open to everybody in the world. So it's a hackathon, global hackathon. And what it does is we are encouraging for you to design systems to help with like natural disaster preparedness and all those like handling natural disaster. And also IBM is teaming up too with other organizations too. So it's really for a good cause, and it's for everybody in the world too. And the good thing about it is that if you win, then you can have money. There's a price associated with it. I think there are like different price level too. So please check it out. You can enter this competition on your own, or maybe form a team up to 5 people. And right now the date is July 29, 2019. So there's still time to sign up for it. So I invite all of you to sign up for that, and it's really for a good cause. So, okay. So thank you again, and thank you very much.